In this video, we're going to expand our register output by pushing or driving our LEDs by way of a line driver. I got a mailbag today and I want to go through some of the components that I got for this build. And then I want to have a quick conversation and start to define our clock cycle. Certain things are going to need to happen at certain times, and I want to start laying that out so we have a frame of reference for when we go to build. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Alright, here's where we left off. I have my clock version 1. I know I'm going to be doing some things to this in the future, but those are a little ways out at this point. I've got the test harness down here for providing input into the registers, and then I've got the register assembly so far here. One of the things I've managed to do, and I did this on purpose to keep the video short, last video, is I have the output connected directly to, so the output being the LEDs here, connected directly to the register output. And what I want to do is I want to actually buffer those. I want to make it such that the output LEDs are not driven by the same signal as the bus itself, to try to keep the bleed off of voltage or power as minimal as possible. And so what I have here is a 74LS541 chip. I'll bring up its pinning here. And as you can see from the pinning, it has inputs and outputs. So inputs are along the bottom, outputs are along the top. It's not as nicely in line as the 574 was, but we can work around that. And then pins 1 and 19 actually control it, both of them being active low. So for this instance, what I'm going to do is I'm going to have the line driver always active so I can always see the LED output. And so to do this, I'm going to disconnect power because I'm not quite that brave with what I'm about to do. What I'm going to do is I'm going to actually pull this LED graph out. I'm going to turn it around. I'm going to place it over here with these current limiting resistors for the LEDs plugged in over here. And I'm starting in the middle here just to make it a little bit easier for me to get everything plugged in correctly. I say as I have trouble plugging something in correctly. So my whole point here is that I want to have the bulk of them, at least 5 of them, going straight from one connection straight down to the other. And then the ones off to the side, on this side going at a slight angle, and anything over here on this side going at a slight angle. I believe there's only going to be one over here. I'll do the rest of those here in a minute, but this allows me to take pin 2 and line pin 2 up with the most significant bit there, and then bringing in some pre-cut wires. If I add ground and then up here add power, and then a couple of extra wires. I don't have them cut for this. Actually, this one should work. Pin 1 gets tied to ground, and then pin 19 gets also tied to ground. And that then should now be able to drive the output over here to this LED. So what I'm going to do is I'm going to work on that real quick. I'm going to get this wired up, get this particular thing cleaned up, make sure I get everything stretched over here, get the resistors moved, and then we'll come back and test it. Now, as I'm doing this work, I said I would clean it up, but I'm actually not going to do clean up. I'm just going to do temporary wire up. So you're going to see a lot of temporary wires jumping between the line driver and the LEDs. And again, the two LEDs that are on the left are the two that are unused, so that I'm using the 8 green LEDs. Okay, so that's wired up. I can apply power again. And that appears to be outputting here the contents of what's on this line driver here, which is the high order byte of the register here. So if I change its input such that every other one is on, you get the output such that every other one is on. I've got down here 10101010 and 10101010. So that works well. Let's put another different pattern in so that we can make sure that we have them distinct. 1110 0101 11100101. That test allows me to make sure that I didn't actually cross anything over up here and wire up the nibbles in the wrong order, which unfortunately I've done in the past. So with that done, what I'm going to do is I'm going to move this over as well out to here, drop in another 74LS541 IC, pull out the resistors, hook up power and ground and the control lines, and get everything then cleaned up. And this will be a rather long fast forward. As I'm looking at this, I'm seeing not 220 ohm resistors. So 102 1000 ohm resistors on here. So I will pull those out and I will replace them with the right value, 220 ohm resistors. Not sure how I made that mistake. And for the record, I don't know the colors that well. There's several patterns I know off the top of my head, like red, black being 220 ohm, and I did not see two reds next to each other, and therefore I did not recognize that as a 220 ohm resistor. Looking at all of those that I moved over earlier, those all look good. Let's slide these out the way. I have this box of hookup wire that I keep outside of the view here. And that's what I'm using to snip all my wires from. So I find if I measure out in these high density wire ups, one or two extra positions in the breadboard, it actually creates just enough slack in the wire up that I can actually fit everything. And it's all basically just a little twist out of the way, but it's enough of movement there that everything actually fits. And fits nicely, I should say. And these wires, I happen to cut exactly the length I need them. I just happen to do that. That doesn't happen often. Coming up at the end of this video clip, I actually got called away. And I paused the video recording as I stepped away and neglected to restart it when I got back. Well, I went back and looked at the video. I tried voiceovers. I tried all kinds of things. I just couldn't find anything that worked well. So It turns out that I got the first wire wired up and missed the 7 additional wires associated with this line driver. And you missed my testing, so I figured it would be okay to just go ahead and redo that. This is somewhat of a reenactment at this point. I did manage to get the decoupling capacitors in, and I've got an entire video on my thinking around the decoupling capacitors. I will link to that in a card up here in the corner. And so you get to watch me do this in real time because I don't have to actually cut wires and I don't have to strip them, and I can actually get this all taken care of here all at once. So then the decoupling capacitors go into power and ground right up next to both pins, the power and ground pin. And yeah, that goes much faster when I've done it once. And then so now it's just a matter of testing. And so if I hit the clock with all of the bits on in my test harness, everything comes on, so that's good. I'm going to turn everything back off again. Pulse the clock again. I missed a pin. Pulse the clock again. This switch never got pulled totally low or off. And so now, grabbing my trusty pin here, I'm going to set a pattern in here. Okay, and once again, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. Okay, so that is actually working the way I expect it to. I got a mailbag today, and I kind of want to go through what I received and show that to you. I did buy a bunch of additional capacitors, and these are, I'll pull these out here. These are 47 microfarad capacitors. They're obviously electrolytics, and of course they're polarized. And I'm not sure if you can see that in the glare. 47 microfarad. And these are going to go on each of the power strips on the boards to try to absorb some of the power spikes at the breadboard level. I got some pins, some more male pins for hooking up the or making the wire ribbons. Excuse me, ribbon cable. I'm not sure where my head's at today. So I managed to get 1, 2, 3, 4, 5 packages of 100, so 500 additional pins. Yeah, I've got a pretty good idea I'm going to be using all of those with all the different bus connections that I'm intending. I did get some solder. And so this is some new solder. If you saw my first video, I'll link to it up here. If you saw my first video, I had a heck of a time with that thick solder. Obviously, this is much thinner. So I will have to feed a lot more in to create the solder connection. But I will have a lot more control over that. Let's see if I can get that on some kind of a white background for you. That is nice and thin. Comparatively speaking, set them up side by side. Yeah, night and day. Maybe too thin, but we'll see. I also found some orange hookup wire, and this I'll end up putting into my box, but this then allows me a new color that I did not have before, so look for its debut on the breadboards. One for my hookup wire box and one for the supplies cabinet. And I've mentioned this before, and I'll mention it again. I buy my breadboards in 2 packs. This is actually Bus Boards BB1660 solderless breadboard. And I buy them this way because they're actually less expensive. It's basically two 830 hookup point breadboards that are shipped bound together. There's actually two metal plates the size of the 830s. Sorry about the glare. And then there's two actual independent breadboards. Even the stickers are separated. So by buying them in a 1660 pack like this, I actually get two full breadboards, and I only have to buy them in pairs. They are actually less expensive. I believe I paid $15 for the 1660 package versus $9 or $8.50 for each one of these individually. So that would have been like $17. So I do end up saving a little bit of money doing that. And that was my mailbag today. Before we get too far into how to control the register, we really should have a brief conversation about what the clock cycle is supposed to look like on this computer. We really have two classes of buses that we're going to be dealing with. One is the address bus, which tells memory what data location to load and assert onto the main bus. And then we've got the data bus or main bus. The main bus is one of the data buses. The data bus that then is going to have the values that will then get latched into registers. So there's 4 parts to a clock cycle. There's the rising edge, there's the high level, there's the falling edge, and there's the low level, and you can see that outlined at the top with the black squares drawn around the green boxes. So on the rising edge, we really want the address bus to assert a value, or registers to be able to assert a value onto the address bus, whereby the memory can stabilize and retrieve that byte of data from memory during the high level. On the falling edge, then the data bus will assert its value, and then during the low level, stabilize that value out on the data bus. And then again on the rising edge, we're going to latch a new value. Now, that could be a new address value, which then gets turned around and gets reasserted back out onto the bus. And then you have the high level to stabilize that. And then the falling edge, the data gets asserted and then stabilized on the low level. And rising edge, the data gets latched. That's the basic clock cycle at this point. Of course, we'll add to that as we add more components into the computer. But with this in mind, then we can start looking at how we want to control data outputting to the address bus and then latching in off of the main bus, or main buses. Yeah, I'm giving a sneak peek there. There's more than one bus for each. Stay tuned for more on that. So with the clock cycle in mind, we'll start looking at address bus 1's line drivers and get those wired up next time. And then we can start thinking a little bit about our register control circuitry, specifically how we're going to assert our address onto address bus 1. We do still have our parked clock tasks, and we'll get to those again in the future at some point. Thank you, and we'll see you soon.